65 million years ago, the Earth suffered a catastrophe so violent that it resulted in the extinction of 3/4 of all species alive at the time. Among them were the dinosaurs, which had evolved over 140 million years. We now believe that a rock the size of a mountain, tens of kilometers across, with a mass of billions of tons, was on collision course with the Earth. It approached at a speed of over 20 kilometers a second, 30 times faster than the fastest aircraft today. As it screamed through the atmosphere, friction with the air heated it until it became as bright as a second sun in the sky. When it struck the Earth, it created a fireball hotter than the surface of the sun. The shock of the collision would have been heard and felt all around the planet. That blast would have flattened anything in its path for thousands of kilometers around. It made a crater 200 kilometers in diameter and threw billions of tons of rock into the atmosphere, darkening the Earth's surface into a night that lasted possibly for years. The rock that eventually fell back to Earth was enough to cover the entire surface of the planet to a depth of over a centimetre. The energy released was greater than all of the world's nuclear bombs detonating at the same time. That collision changed the world in an instant. If it hadn't have happened, it's quite likely that descendants of giant dinosaurs, like this Diplodocus here, would still be roaming the world, and the human race would never have had a chance to evolve. Fortunately for us, that kind of massive collision happens only very rarely, but it's a spectacular example of one of the basic scientific principles, that a moving mass has energy, and the bigger the mass, the more energy it has. Energy is a word we use every day. I mean, if I say that I'm feeling full of energy, or we need to save energy, then you know what I mean. And that's fine for everyday use. But in a scientific statement, I'd probably want to use the word a bit more precisely. To a scientist, the concept of energy is a way of looking at the world and making sense of what we see. It's a way of describing changes. It helps us to explain what we observe and to predict what will happen. Let's take a very simple example. Now, with apologies to poor old Diplodocus here, what I've done is to compress a spring inside the toy dinosaur. As the spring released, transferred energy into the dinosaur and made it move. What happened was that I transferred energy from my body into the spring, and then the stored energy in the spring was transferred into the movement of the toy. But curiously, we haven't actually seen any energy at all. What we've seen is the effect of energy being transferred. If we'd been able to send up a satellite to transmit pictures of that asteroid while it was still in outer space, we wouldn't have been able to see the energy that it was destined to deliver to the Earth. It was only when it collided with the Earth that we would have been aware that it had so much energy. What we would have seen and felt is the result of energy being transferred into other objects. Some of the energy went into lighting up the sky. Some of it resounded for thousands of kilometers. Some of it made other things move, the rocks that it hurled into the air, and the shockwave that travelled through the Earth. And the rest of the energy went into heating the surface of the Earth. But it's not only asteroids that get hot on impact. It's part of our everyday experience. Cassie Jackman is one of our top squash professionals. We caught up with her at a sports club in London, training for the match we've just seen her winning.
Now, I like to think that I'm quite good at squash, but the professionals are in a completely different class. And Cassie Jackman is rated world number 3 squash professional. Cassie, hi.
Cassie, now I know it's important that the ball's warm before you play. Why is it?
Well, obviously when the ball's cold, you bounce it, it just doesn't bounce. So you need the ball a lot warmer for a match so it's at the right temperature.
And how do you warm it up?
Just giving it a few hard hits against the wall for a few minutes, that should get it to the right temperature.
Okay, well, before we do that, can I take the temperature of it with this temperature gun here? We've got 24 degrees centigrade. Okay, thank you. I'll let you do your stuff.
Okay.
Right, can I feel now? That's amazing, isn't it? It's really hot. And just from you hitting it and it hitting the wall.
Yeah,
Let's have a look what it is now.
That's amazing. That's over 40 degrees in such a short space of time. I mean, what sort of temperatures would you expect a ball to get in a match?
I think the average temperature for a match in an amateur game is probably about 45 degrees, but it has been known to get up to 55 in perhaps a professional match. So it's really hot.
That's almost too hot to touch, isn't it?
Yeah, nearly,
Wow.
yeah.
We can't see the energy, of course, but we can do the next best thing. What we've got here is a special camera. And what's special about it is that it doesn't respond to light like an ordinary video camera does, but to heat. Just to show you what I mean. When I take my hand away from the wall, the infrared camera can still see where it's been, because I've transferred some of the heat in my hand into the wall of the squash court. I'm going to ask Cassie to warm up another squash ball now. Is that okay, Cassie?
Yeah, sure.
But this time, we're going to film it with the infrared camera as well as the video camera. I'm going to get out of the way first. The colour flashes you see are the camera picking up the temperature as the ball warms up. The whiter the colour, the hotter it is. So why does the ball get so hot? It's moving at 40 metres a second, so let's slow it right down. The time it takes for the ball to travel this distance is about 1/100th of a second. We've slowed it down 300 times. When the ball hits the wall, it decelerates suddenly and is forced to change shape, almost to a disc. This shakes up all the molecules in the ball and makes them move around faster. We feel that as heat. With the infrared camera on its most sensitive setting, we can even see that the hot ball, like my hand earlier, is transferring some of its energy into the wall. It's making the wall very slightly warmer where it's hitting it. We can track the energy in the moving squash ball back to its source. Cassie could only hit the ball as hard as she did because she had some energy, and that comes from the food we eat. We transfer that stored energy into active energy when we run, play squash, or even sit watching television. So the first link in our energy trail is from the moving squash ball to Cassie. Cassie got her energy from food, and that came from plants. Plants store energy from sunlight, so the source of the energy in the moving squash ball is the sun.
This is Manchester Town Hall, but I haven't come here to look at the outside of the building. I've been set a challenge to wind the clock. We're not quite there yet, But you can see how the big clock works much more easily by looking at this smaller clock. Now, the clock's mechanism is turned by the force of gravity acting on this mass that we call the clock's weight. At the moment, the weight's resting at the bottom and the clock is stopped. There's no energy in the system. So let's give it some. The clock has now started working and will go on working until the weight has moved down to the bottom again. As the weight moves, it moves all the wheels inside the clock. The pendulum stops it moving too fast.
Just as with the toy dinosaur at the beginning of the programme, I have transferred some energy out of me and into a machine. The clock has a little more energy and I have a little less. Let's hope I've got enough for the big challenge.
Wow, this must be the mechanism. And this is Andy Hames, who looks after the clock. Hi, Andy.
Hi, Helen.
Incredibly complicated, isn't it?
It is, yes.
How old is the clock?
It's 117 years old, and it was made in 1877. The clock mechanism is effectively in three separate sections. That section is the hour strike, which counts the hours. That section is the actual clock mechanism, and the far section is the chimes that does the Westminster chime.
What's that?
Well, that'll actually sound every quarter hour.
Clocks like this work with weights, don't they? I can't see any weights here. Where are they?
There's three separate weights, one for each mechanism, and they're in shafts around the tower.
Can I see one?
Certainly, yes.
Now
That's
that
one of
looks
them.
heavy. How much does that weigh?
That weighs around about 100 weight.
Wow, that's about 50 kilos, nearly as much as I weigh.
Mm-hmm.
And how many of those do you have?
There's 12 on the main weight.
Do you want to put it down?
Yes, please.
So 12 of these for each.
There's 12 on the main works, and there's about 18 on the other two that operate the bells.
Gosh, so in total we're looking at over 3 tons
That's
of
right.
weights. Now that's very heavy. How do you wind up something like that?
Would you like to try it?
Here goes. Oh. This is much more effort than that small clock downstairs.
Yes, yeah.
How many times do I have to wind this?
About 400.
400 times. How long is that going to take me?
You can do it in 40 minutes, but at that rate it'll take much longer.
Oh, because I'm going slower than you do it.
That's right, yeah.
Now, each time I move it round once, how far does that pull up the weights?
About 4 inches.
10 centimetres, yeah?
That's right.
And how high up do they have to go altogether?
120 feet.
35 metres, that's all the way up the tower, yes?
Yes.
Oh. Well, I hope they're gaining lots of potential energy, because I'm losing lots of my energy, I tell you. Oh. Well, I am now thoroughly exhausted. I've transferred energy from my body to the potential energy of the weights. They're now at the top of the tower. So, as those weights move down, of course, they're moving the mechanism of the clock, and that in turn turns round the hands. Andy, how long is it going to take for the weights to move all the way down the tower again?
About 8 days.
So you have to wind this every week?
No. These days it's done with an electric motor. So every hour a cam comes round on here, closes this switch, and it winds up.
The energy stored in the clock's weights came from me, and like Cassie, I got my energy from the food I ate, and that can be traced back to the sun. But the clock is now wound by electricity. Can that too be traced back to the sun?
For our third energy trail, we've come to a disused gravel pit near Doncaster. It isn't used for gravel anymore. It's now got another use. Look at this. Racing's all over now and everyone's gone home. All that is, except for one person. This is Ed Bradley here, and he's going to teach me a thing or two about motocross racing. Hi, Ed.
Hi, Helen.
That looked absolutely wonderful. What amazes me is how you actually manage to go round the corners without sliding over the top. I mean, how do you manage that?
We use the banks as we're coming into the turns, and we lean ourselves into the corner to match the angle of the bank.
Now, Ed, this looks completely different to any of the road bikes that I'm used to. What are the main differences between motocross and road bikes?
Okay, and the main difference is that the suspension, you've got a lot more travel there on the front and the back, because the tracks are generally rougher than a road. The tyres have got knobbles on them, whereas on road tyres they're just little grooves. On the track where it's muddy and grip, you need a lot of grip, so the tyres get the grip. The acceleration is a lot harder on a motocross bike than a road bike, because we're trying to get out of the corners quicker.
You mean it's faster?
Yeah. And the general layout is more for a racing position rather than a comfortable position, whereas on a road bike you're trying to be in a comfortable position.
It's a wonderful piece of machinery, and you make riding it look so easy.
It has become easy over the years, and if you want to have a go then, let's see how easy it is for you.
Really?
Yeah.
Come on then.
Okay.
Whoa. This is very slippery. The back wheel feels like it's moving all over the place. Right, now I've got to remember, it said slow down for the corners, rake both brakes. Right, now then, put your leg out in case you come off. Oh dear. Over the bump, see if I can stand up to absorb some of the impact. And it's the energy of the impact on me. Right, this is actually much more difficult than it looks, but really, I think I could quite get into this, you know. The bumps are the best thing. There we go. Oh, thank you. Oh, hot and hard work, but brilliant fun, isn't it? Thank you for the tips. I mean, they were really useful, but it's still difficult, and for now I'm going to leave it to the expert.
For the bike to move, we needed to put in some fuel. There's masses of energy stored in petrol. The bike transfers the stored energy in the petrol into active energy. The bike moves and the mud flies. Some of the energy is transferred into sound. After the race, parts of the bike are still hot, and that heat will be transferred into the air as it cools. We've done a lot of detective work in this programme, tracking energy transfers. Most of the energy trails start with the sun and finish with heat in the environment. But is that the end of the story? Where does the energy go after that? What happens when the dust from the asteroid impact has settled? When the squash ball has cooled down, the clock stopped, and the bikes run out of petrol?
Well, we might think that that would be the end of the story, that the energy trail has simply gone cold. And that often seems to fit with the way things appear. Up to about 150 years ago, people were quite happy with the idea that if they couldn't see any changes anymore, then the energy had been used up and no longer existed. It had gone. It's difficult to imagine that there might be another way to explain things. But sometimes what we understand about science doesn't always agree with what we notice going on around us every day. But then, here in Manchester, a scientist called James Joule, who at the time looked rather younger than he does in this statue, did some experiments that changed the whole course of science. Joule was the first person to make the real scientific connection between work and heat. If you like, how hard we hit the squash ball and how hot it gets.
Joule made detailed measurements of the increase in temperature that he noticed when something is hit or when a liquid is stirred. His work paved the way for later scientists to make the last link in the chain, where that energy goes when something loses heat, when it cools down.
If James Joule could look at our squash ball at the end of a match, he would say that as the ball cooled down, it warmed the air around it very slightly. And that very slightly warmer air transferred its heat to the slightly colder air around it.
Another way of looking at this is to imagine a person with £1 million. They can do many things with their money. If they give it away, £1 each to 1 million people, each person can do very little with that share. But although the money has become spread out, the total amount remains the same, £1 million. It hasn't been destroyed. But it's the same with energy.
We now believe that energy is never used up or destroyed. It just spreads more and more thinly into the environment.
James Joule's work led to a conclusion that even today stretches our imagination to the limit. If we believe that energy can never really be created or destroyed, it follows that when I throw this pebble into the pond, the ripples never really die away.